Hello and welcome back. In this video, on the next couple of videos, we will look at some topics in unsupervised learning, specifically at the most popular K-means algorithm and as well as the hierarchical agglomerative clustering algorithm. So, some of these slides are provided by Intel software based on their curriculum offering, and many of the much of the content is also inspired by the text Introduction to Statistical Learning as well as the elements of statistical learning text. So, a brief overview of unsupervised learning is in order. So far we have looked at a variety of techniques which can be classified as supervised learning algorithms, in the sense that you are provided with a bunch of inputs, primarily features as we like to call them, and we have a corresponding label to each one of those inputs. So, it is either a category label or sometimes it is just a real number, which means more like a regression problem. In all those cases that we have seen, for a given x, which is just a raw input or some features which have been extracted from the input, there is a corresponding output y, which is either a label or some real valued number in the case of regression. However, in the case of unsupervised learning, we are just given plain unlabeled data. Now, this is the case in most of the time in the real world, because labeled data is hard to come by. So, we will be given a bunch of unlabeled data, and the idea is to develop a model from the data itself based on some metric that we define. Based on some metric, we develop a model which automatically separates the data into different classes or different bins, if you can like to call them, and that is it determines a structure. The unsupervised learning algorithm determines a structure from the model leading to the model, and whenever there is new unlabeled data, we run it through the model to see in which one of those bins or clusters that it falls, or we extract an underlying structure based on the model. So, this is the general flow of a unsupervised learning algorithm. So, for instance, topic modeling. So, we are given a bunch of text articles, maybe these are newspaper articles consisting of unknown topics, right. So, based on the text in the articles, we come up with a model which tells you, which separates the articles into several topics. Okay. So, we do not know what the topics are primarily, but because they are themselves are extracted from the given text. However, when a new article comes in, which is basically we have a new with an unknown topic, we run it through the model and then it binds it with similar articles, that is, it predicts what class it would typically belong to. Okay. So, this kind of structure is what is commonly called as unsupervised learning, wherein we really do not know what the classes are or what the underlying structure of the data is, except that we are given the raw data, and then we try to develop a model based by finding some underlying structure to the data. Okay. So, this structure is again dependent on some metric that we define, as we will see for the K-means algorithm as well as the clustering algorithms, other clustering algorithms. So, for K-means clustering, here is a brief overview. So, here are the statistics of so this is basically we gather statistics. Let us say there is a website web application and we gather statistics of the users that use the web application. So, one such statistics is the age of the user, right. And let us say we have like several users, in this case about 5 or 13 or 14 users, and we just we plot their age along an axis, that is right there, and it is very obvious from the plot itself that there are two visually obvious groups in the user's age, right, based on the user's age. So, that we can see here, the green is one group and the red ones form another group. Well, let us consider a slightly more complicated, in this case 2D. Now, typically in an unsupervised setting, or in this case a K-means algorithm setting, you will have a lot more features, in this case income and age are features. So, you will have a lot more, in input dimensionality would be typically higher, but for the case of illustration and understanding the algorithm, we will just consider two features, which are the income and the age and the income, right. So, right now what we will say is that we say that there are two clusters. Okay. So, when we plot the data, it becomes obvious that there are two clusters, very obvious two clusters, but in many unsupervised learning algorithms, the number of such clusters is also unknown, especially for K-means. Wherever you use K-means, the number of clusters is also typically unknown. So, but that is another kind of an hyperparameter that you would have to determine. But in this case, let us say we want to separate 2 clusters. So, what we do? So, we initialize 2 cluster centers, so to speak, right. So, these are the 2 cluster centers that we have initialized, correct. And so, this is random, and again we can make some very clever guesses of the initial centers based on the data itself. But right now we just say we will pick 2 cluster centers at random, and of course, when I say at random, it depends on the range of your data. So, you have to pick that again something which is a rational choice of the cluster centers. So, we randomly assign it, and what we do is we move each center to the cluster's mean, right. So, what does that mean here? So, we assign 2 randomly chosen cluster centers, right, and following which what we do is we calculate the distance of each one of these data points. So, there are several data points. Again, initially we do not know what clusters they are in. So, we would calculate the distance, in this case Euclidean distance, let us say Euclidean distance between the cluster centers and each one of the data points, and assign the data points to the cluster center which is closest, right. So, for instance, this particular data point is closest to this cluster center as opposed to that one, and so we would assign this data point to this cluster center. So, similarly we would go across the data set and assign each one of those points to the corresponding cluster centers which is closest to them, right. So, then once we do that, we would get 2 different sets of clusters, green and blue in this case, following which we would recalculate the cluster center based on the membership, right. So, now we have all these green points which have now been assigned to, remember our initial guess was somewhere here for the green, and after we have assigned the closest points to that cluster center, we would recalculate the mean of the clusters of the points in the cluster. So, to get a new cluster center here, these are the new cluster centers for the green and the blue. Once again we would redo this calculation that we did earlier, that is reassign by calculating the distance of each one of those points to the new cluster center, and then reassign the label accordingly. So, then you see that the label has changed dramatically from here to there, and then we would once again recalculate the cluster center based on the new labeling. So, we continue this till the cluster centers do not change significantly, and then we stop right there, and so now we have the membership belonging to the clusters, right. So, we can also set k equal to 3 and do the same calculation as we outlined before, and we can get about 3 clusters, in this case red, blue and green. And the problem is with K-means is that it is very sensitive to the initialization. So, we can have a completely different initialization of the cluster centers and end up with a different clustering set. So, it is the same data set. So, we had this red, blue and green clusters, and with a different initialization we will get something like this, okay, which is different from the previous clustering that we obtained. So, this is very sensitive to the initial conditions, right. So, we will see later as to how we can resolve this problem, that is how do we decide which one of the cluster centers is correct and which one we should discard. Okay, so, here is one more example of k equal to 3, here once again k equal to 3, and we have a different starting point or the initial values of the cluster centers, and we got different set of clusters, right. So, to summarize, to put it formally, the K-means algorithm is obtained by actually minimizing a cost function, so which is shown right here. So, that is the cost function, so that we are trying to minimize. So, its W is what is called the interclass or the intra-class variance. Okay. So, we will see what that is soon. So, what is this trying to optimize? The idea is to optimize the assignment of each of the data points to a cluster center, so that this cost function is optimized. So, this is a combinatorial optimization problem. So, remember it is this cost function is minimized by assigning the appropriate label to each one of the data points. So, let us say we have data points x1, x2 up to xn, and we have k classes. In this case, let us say k is like 1, 2, we say 2 classes. So, there are labels 1 and 2. So, the optimization problem is to figure out the right assignment. So, we will say x1 is 1, x2 is 1, x3 is 2, so on and so forth, xn is some class 1 again. So, this arrangement here is the outcome of the optimization. So, what is the correct arrangement of these labels, so that this intra-class variance is optimized. So, that is the problem that we are trying to solve. So, we will write this out little bit more detail. So, we see that the intra-class variance is defined by this formula. It is nothing but here P in this summation is the number of features in your input data. So, x, so if you have a data point x1, right, if there are p features, then each data point has x112, x1p features, right. So, given a particular class Ck, so in this particular summation, what you are trying to do is determine the distance between, so this is xij minus xi prime j. So, where I and I prime are the data point labels inside a particular cluster. Okay. So, let us say we have an initial clustering and we are looking at only the elements in that cluster, and we are calculating the sum of these distances between the elements in that cluster, right. And we do so for all the clusters, and every time we would divide by the number of elements in that cluster, right. So, this is the variance or intra-class variance that we are trying to minimize. We can rewrite this formula as xij minus xkj bar, where xkj bar is the mean of feature where is the mean of the cluster, sorry, which is also known as the cluster centroid. So, it is the mean of the cluster k, right, and j is the data the feature index, right. So, xij is the ith element in cluster Ck and its jth feature, and xkj bar is the mean of the jth feature in cluster K, right. So, that I hope that is clear. So, xij is the ith data in cluster Ck and j is the feature index. So, similarly, xkj bar would be the mean of jth feature in the cluster Ck, right. So, that is what we are trying to do here. So, it's basically you can rewrite this formula this way, and this is the cost function we are trying to optimize. There will be one more summation if you bring this summation down there, there is one more summation here. So, that is the cost function we are trying to optimize. So, it is a combinatorial optimization problem. So, it is non trivial to do. So, we use like a greedy approach or something called iterative descent, that is what is commonly referred to as the K-means algorithm. So, just to clarify the notation again, the data samples are indicated by x1 to xn, there are n data samples, there are k clusters and the cluster index is small k, cluster index is small k. So, and we want to split the data into k clusters where each cluster is denoted by Ck, right. So, Ck is just a set of all the data point indices which correspond to that cluster, right. So, because the data point indices range from x1 to xn. So, class C1 cluster C1 would be just a set of indices of the data points. So, which basically, so let us say data point 1, 5 and 20 are in cluster C1. So, that is just C1, right. And there are other properties, all the Ck do not have an intersection, So, one data point will only be strictly assigned to one cluster, and the union of all the clusters will give you the entire data set, right. So, the idea again is to, as I mentioned earlier, is to assign the data to cluster centers such that within cluster variance, that is the distance, the squared distance between the elements or the data points in that cluster is minimized. So, that is how that is the assignment problem that we are trying to solve. Okay, to summarize the algorithm, so I just rephrase it differently, said that randomly assign cluster index to all the data points, which is the same as saying you choose a cluster centroid first, and based on the distance to that centroid you would assign a index, cluster index to each one of the data points. So, in the first step, the loss function that we had mentioned earlier and have reproduced here for convenience is minimized with respect to the mean value of the cluster, right. So, we would determine the mean value of the of each of the clusters based on the data points in it, and in the second step, given the cluster means, you can minimize the cost function further by reassigning each point to the closest cluster mean. Okay. So, this is done repeatedly, and you can see that in each iteration the cost function, the value of the loss function will be minimized till a point wherein there is no appreciable change in the cluster center locations you would iterate. Okay. So, this is one of the more commonly used algorithm, also refers to the Kmeans algorithm. There are other ways of solving this optimization problem also. So, the earlier question we had is how do you determine the best possible value of k. Okay. So, that is not a question that is easily answered. So, typically what one would do is to plot this W that we mentioned, the intra-class within class variance that we calculate as part of the optimization. We plot that for the final optimized value, we plot that as a function of k, here this is k, right. And then typically you can notice this knee. So, wherein once beyond a point the W value decreases, but not as much. So, you will have a knee in your plot, this inflection point, and we choose the k corresponding to that inflection point. So, that is k that is chosen. So, there is another problem that we also talked about, that is wherein we were saying that if we had different initialization, then we would end up with typically different clusters, right. So, then how do you figure out which is the best possible cluster to best possible clustering that we have obtained. Now, in order to do again we would do the same strategy, that is we look at the cost function, the loss function that we calculated, and choose the cluster with the least value, choose the clustering result with the least W value. So, that is the solution to that problem. However, the choice of k sometimes will be given, and sometimes one has to discern it from the data itself. So, it is basically very data dependent, and so generally there is not too much work being done in this area, because it is something that is kind of outside the algorithm itself. So, let us look at the cost function or the loss function that is optimized by the K-means algorithm. Okay. So, we will set up the problem first. So, initially we are given data samples x1 to xn. Okay. So, 1 to n the indices of the data samples. We decide that there are k clusters in the data. Typically sometimes this is given, k is given, and sometimes we have to discern from the data itself. So, the cluster index goes from 1 to capital K, okay. And of course, what we saw earlier was that we want to split the data into k clusters, and each cluster is given by Ck. Okay. So, what does Ck contain? So, Ck has the indices of the data points. Okay. So, let us say data x1, x3 or x100, if n is let us say 1000, all belong to class C1. So, since C1 will have the indices 1, 3 and 100. Okay. So, that is how we would define the Ck. So, we want to split the data into k sets, and the k sets do not have any intersection. So, intersection of any of the Ck, any two Ck would be a null set, and the union of all the Ck's would be the entire data set that you are using. Okay. And how do we optimize, how do we pose this as an optimization problem? So, we want to assign data samples to clusters such that the within cluster variance is minimized. So, we can think of the within cluster variance as the sum or the average distance between the members of that cluster, between the data points in that cluster, the distance in terms of Euclidean distance, right. So, if we were to pose this formally, this is the optimization problem that we are trying to solve, where W is the within cluster variance. So, it is right there, cluster variance, and we want to take the sum over all the clusters, k clusters. So, for each cluster we calculate this W, which is the within cluster variance, and we take the sum over all the clusters. Of course, what are we trying to do in the process? We are trying to figure out the assignment of the data points to the clusters, that is what we saw here earlier, right, such that this sum is minimized. Okay. So, that is our optimization problem. This W itself can be written in this form, wherein here the inner summation j runs through the features. So, if it is one dimension, the data set one dimensional, that is you are just given n data points, and each data point is just a scalar value. Sometimes if you have n data points, each data point can be a vector of values, which the size length of the vector being p, right. So, the inner sum runs over the p features. So, we calculate the distance, Euclidean distance between two data points I and I prime belonging to a particular cluster k, right. And so, for each data point, pairs of data points I and I prime, we calculate the Euclidean distance between them by summing over its feature distances, and of course, we take the mean value for every cluster, right. This is the cost function for the single cluster, and of course, we have to sum this over all the k clusters. It is possible to rewrite this particular cost function in this form. So, here if we look at this x I j, the inner summation, where j is the feature index. So, x I j is basically the ith data point, jth feature in cluster Ck, right, and x k j bar, the average, it is basically the mean of feature j in cluster Ck, correct. Okay. It is a mean. So, we are just trying to, as we saw earlier in the illustrations, we are just trying to find the distance of every data point within a cluster to the center or the cluster mean, and we sum over all the distances inside a cluster, and then we do the same for every cluster that we have figured out, and we add them all up. And what the optimization problem solves is that we figure out the correct assignment of the data points to the cluster such that the summation that we calculated is optimized. Okay. So, if you were to pose this as an algorithm and you are trying to solve it, this is a combinatorial optimization problem, and the way to solve it would be an iterative technique, it is called iterative descent. So, one way of looking at it is we randomly assign cluster index to all the data points, right. So, let us say we have clay number of clusters is k, capital K, then we would assign at random a cluster index to each one of the data points. So, the first step is to minimize the loss function with respect to the mean value of the cluster. So, we know that once we the way to minimize the loss function is to figure out the distance of each one of those points from the cluster centers, right. That would minimize this cost function that we saw earlier. Now, once the cluster center is determined, the second step would be to recalculate the distance of all the data points to each one of the cluster centers and then reassign the data points to the appropriate clusters, that the cluster to which the distance is the smallest. So, we go back and forth between these two steps and till there is convergence, in the sense that the cluster centers stop changing.